2.4 chemical reaction. Be able to identify the reactants and the products of the chemical reaction. Explain what is activation energy. Compare and contrast exothermic and endothermic reactions. That's what I expect you to be able to do from section 2.4 in your textbook. You can see that I don't really assign reading too often, so you're expected to just read the section so that you have a good foundation on your own. Okay, so make sure you do that. Go ahead and fill in your notes. Alright, so chemical reactions, which is your first vocabulary term, changing substances by breaking and forming bonds. So whenever you start with something and you end with something new, the molecules have undergone a chemical reaction, and that takes breaking bonds and forming new ones, and possibly different ones. The formula I've given here, or the chemical reaction I've given you here written out, is 6 molecules of oxygen plus glucose gives you 6 molecules of carbon dioxide and 6 molecules of water. That is the formula for cellular respiration. You don't have to have that memorized now, but in the future you will. Today we're focusing on vocabulary, reactants, knowing what a reactant is. Reactants are substances changed during an experiment. It goes with the name. Reactants do the reacting. So it's the stuff you put into the chemical reaction, and in this case we put 6 molecules of oxygen and 1 molecule of glucose. That is what's going into the reaction, so they are called the reactants. The arrow shows you the direction of this experiment. This reaction is going to go in the forward direction only. And it's going to make your products, think about what you've produced. Products are produced, or sometimes I tell you guys, the arrow points to the product, P to P. And so your products are 6 molecules of carbon dioxide and 6 molecules of water. Sometimes arrows can look like this. They are even in size and they're going in both directions. That means you've reached a state of equilibrium. Some reactions do that. And so it's equally going in both directions. You've reached a balance, and it is known as equilibrium. Some other chemical reactions may look like this, which means that it favors going in the forward direction. However, it can sometimes go in the backwards direction. So it can go forward and backward, but just not as much as going to go backwards. So those are your first 3 vocabulary words. I put this here to see if you can practice the skill, because you need to be able to identify your reactants and identify products. Alyssa?
What's the arrows that one's bigger,
One's bigger is just telling you that if this were right here, it's telling you that the reaction favors going forward. However, it can go backwards. It's just not going to happen that often. So anybody would like to try and practice identifying the reactants and the products in this reaction? This is calcium carbonate gives you, or you can say CaCO3 gives you calcium oxide, CaO, plus carbon dioxide, or CO2. Anthony, you want to try?
Yeah. The Ca stands for what? Calcium?
Calcium.
The calcium, the CO, the 3 the CO2. That stands for CO2, right?
So CaCO3?
Yeah.
So you could just read it straight off. CaCO3. What about that?
Is the reactant.
Okay, so these are your reactants. And so does that make this automatically our product?
Yes.
Yes. So the arrow always points to your product. So in this reaction, we put into the reaction calcium carbonate, and out came calcium oxide and carbon dioxide. Okay? Your next terms is kind of blocked by the thing, but here it says bond energy. Go ahead and write all of it in the bond energy box. And then here is chemical equilibrium. And you're going to include that a double arrow is what represents it. And equilibrium is when a reaction takes place at equal rates in both directions. All right. Bond energy is the amount of energy it takes to break a bond between two atoms or even to form a bond as well. You have to understand that no matter the molecule, I'm going to just draw water. So the hydrogen, so the polar covalent bond between the oxygen and the hydrogen, it's a pretty strong bond. So it takes energy to break that bond. So to break that bond, the molecule needs to absorb energy from its environment to be able to break. And sometimes we add a little energy ourselves by like heating up the stove to increase the chance of boiling, things like that. So energy is released when bonds form. Energy is absorbed when bonds break. A lot of us think when bonds break, energy is released, because you think about it, breaking, release, but it's not like that. You have to scratch that. Energy is released when bonds form. Energy is absorbed when bonds break, because you need that energy to even break the bond in the first place. Now, all scientists have studied this. They've made reference lists as far as what is the bond energy, because it depends. If it's liquid form or solid form, changes the bond energy. If the bond is between an oxygen and a hydrogen, there's a different amount of energy compared to being between a hydrogen and a hydrogen. So even depending which molecules or atoms are there, changes your bond energy. Now, equilibrium, I've already talked about. Good equilibrium, again, is represented by a double arrow. And this is showing you how constantly water, if at the right temperature, can constantly go from the liquid state into the gas state, hydrogen gas and oxygen gas, back and forth, back and forth. No. Okay, next one is activation energy. I want you to add this definition to your notes because it's not on there. There's no place for it. However, it's a very important word. Activation energy. It is the amount of energy needed to be absorbed for a chemical reaction to take place. Okay, so activation is the amount of energy needed to be absorbed for a chemical reaction to take place. So if we look at this graph right here, you need to become familiar with an activation energy graph or a chemical reaction graph. Here on the side, we're measuring amount of energy. So it goes from low energy to high amounts of energy. Then over here, we're measuring the reaction progress. So this is the start of the reaction to the end of the reaction. So for a reaction to even take place, you have your reactants. And here, let's assume every line is 1. So 1, 2, 3. We're looking at a 3 joule, this is all made up numbers, okay? 3 joule bond energy, for example. We need to absorb a certain amount of energy to be able to break those bonds. The amount of energy you need to even begin this reaction, that top of the hill marks where you're going to start to begin the reaction. To even start this reaction, that amount of energy you need is called, the activation energy. Okay, so the top of the hill is the activation energy. We need to know that. Now, the first two types of reactions are exothermic and endothermic. On your notes, exothermic comes first, so I'm going to drop these out of the screen. Put this one up here. Drop this like this. I want you to add the definition to the side of the chart. Exothermic reactions are chemical reactions that release more energy than they absorb. So they are going to give off more energy than they needed to begin with. So for example, in exothermic reactions, the reactants have a higher bond energy, so they have more energy in their bonds than is needed to make the products, because the products have a lower bond energy. So there is a slight difference between the bond energies. So we have a higher bond energy in the reactants, a lower bond energy in the product. So let's assume, let's use some numbers, 1, 2, 3, 4, and we've got 2, 1, 2 over here. So how much do I have left over? 2, right? I've got 2 joules of energy extra. Where is that energy going to go? Where do you think that energy is going to go? If I only need, of the 4 joules of energy I have available from the reactants, all I need are 2 of those joules of energy to actually make the product. Where did the extra 2 joules of energy go? Yes, John? To the environment. So these reactions actually release more energy. That's the definition. They release more energy than they needed to absorb for this reaction to take place. So they're going to release that extra energy to the environment. These reactions tend to feel hot. They give off heat. They can be combustion reactions, which are explosive. Anything that gives off energy to create its product is considered an exothermic reaction. And the reason for that is because the products have a lower bond energy than the reactants. Question? Hey, Kate.
So what would be an example of an exothermic reaction?
Good thing you asked that. I have one for you. Any other questions?
What is the label of the
Yes, of course.
what is like the sun?
The sun, total energy released. All right.
Whoa.
Yep. No. All right, here's your next one.
Okay.
Take the whole thing and
Alright guys, may I have your attention please? Go ahead and fill in the bottom half of your notes, include the definition, and fill in your picture. Notice the difference is the bond energy. The reactants now have a lower bond energy than the products. So basically what happens here in endo, inside, going in, endothermic reactions, 1, 2, 3, 4. The products are 1, 2, 3, 4, 5, 6. So now we're missing 2 joules of energy. So we have 4 joules of energy to begin with, but what we want to make needs 6 joules of energy. Where do we get the extra 2 joules of energy?
From the environment.
From the environment. So you need to absorb more energy than you release. Because you are absorbing energy from your environment, when you take energy out of a place, you make it feel cooler. So most endothermic reactions feel cool to the touch or cold because they're taking the energy that they need to make their product from the environment. Seconds. Oh, guys, please remember to bring cans for the pep rally. Next Friday is the last day. We've only had 6 people. We've had 6 cans brought in by Asante and Alyssa, so you guys need 44 cans by next Friday if we want to go to the pep rally. I keep forgetting to tell you, so please bring in your. And it doesn't have to be cans. It can be boxes of pasta, no pancake mix, things like that. Have it?
You didn't let me go because we were watching it.
Oh, you see, that was supposed to be like 2 weeks ago. I should have deleted video what happened. It's too fun. Devontae just left.